Ever wonder how a single photo can reveal the hidden 3D structure of the world? That's the magic of monocular depth estimation, the science of figuring out how far away objects are in a picture just by looking at them. It's like giving a flat image a sense of space, and it's revolutionizing everything from self-driving cars to virtual reality. But here's the catch. A single image doesn't come with built-in depth data. So how do computers guess what's close and what's far? Let's break it down. Traditional methods relied on handcrafted rules, like analyzing shadows or perspective lines. But today, deep learning is the star. Neural networks, especially those inspired by how our brains process visuals, now tackle this challenge. Think of them as detectives, searching for clues in pixels. They might look for edges, textures, or even how light interacts with surfaces to infer depth. Recent breakthroughs. They're wild. Researchers are repurposing tools like diffusion models, originally designed for generating art, to dream depth maps. Others are using transformers, the same tech behind AI chatbots, to spot patterns across entire images. And some are even borrowing tricks from self-supervised learning, where models learn by solving puzzles in the data itself, without needing labeled examples. One game changer. The rise of large-scale datasets. Projects like HyperSim and Sun RGBD give AI millions of images with known depth, teaching it to recognize subtle cues. But here's the kicker. These models still struggle with tricky scenarios. Think fog, reflective surfaces, or objects that look similar but are at different distances. Enter TR2M, a breakthrough that's changing the game. Instead of relying solely on images, it uses text descriptions as a cheat code. Imagine looking at a photo of a kitchen and reading, "A sunny kitchen with a counter and cabinets." The text gives context, while the image provides visual details. Together, they act like a GPS for depth. Here's how it works. TR2M creates two magical maps. The scale map figures out the real-world size of the scene, like knowing a room is small or vast. The shift map adjusts depth values to match that scale. It's like taking a blurry sketch and turning it into a precise blueprint. What makes TR2M superpowerworthy? It's lightweight. Unlike other models that need massive datasets or sensors, it uses text, a clue we all have access to. And it's adaptable. It can tackle new environments without extra training, like figuring out the scale of a medical scan just by reading a description. Why does this matter? Picture a robot exploring a disaster site. With TR2M, it could know not just there's a wall ahead, but the wall is 5 meters away, crucial for safe navigation. Or imagine placing virtual furniture in your living room with exact proportions. TR2M isn't just a tech fix, it's a leap towards smarter, more adaptable AI. By blending vision and language, it's opening doors to applications we're only just starting to imagine. And that's the power of thinking outside the box, or should we say, outside the camera lens. Now let's get technical. How does TR2M actually work? The key innovation is a framework that combines vision and language. Think of it like a teamwork between two experts, one who sees the image and another who reads the description. They use a technique called contrastive learning, comparing features from the image and text to find patterns. If the text mentions a large wooden bed, the model learns to map that to specific depth cues, like the bed's size relative to other objects. Here's where it gets technical but super cool. They used a least squares criterion to align estimated depth maps with real-world measurements. Imagine you're adjusting a blurry photo. You tweak the focus until everything snaps into place. Similarly, the model fine-tunes its depth predictions by minimizing errors between its guesses and the language-generated clues. They also introduced a pseudo-metric depth step, which acts like a sanity check, ensuring the AI doesn't just guess but understands the scene's geometry. The proof is in the pudding. On datasets like NYU Depth V2 indoor scenes and C3VD surgical videos, their method outperformed previous models. For example, in a colon surgery scene, where traditional AI struggles to differentiate between similar textures, TR2M used descriptions like descending colon with texture type 2 to nail the depth. It even beats state-of-the-art models like EndoDAC in some metrics, without needing special training on surgical data. This isn't just an incremental improvement. It's a paradigm shift. By leveraging language as a contextual anchor, TR2M solves the scale ambiguity problem that's plagued monocular depth estimation for decades. Whether it's a robot navigating a cluttered warehouse or a surgeon analyzing a 3D reconstruction, this tech is paving the way for AI that truly understands the world, not just sees it. So next time you look at a photo, remember, behind that flat image, there's a whole hidden dimension waiting to be uncovered. And thanks to breakthroughs like TR2M, we're getting closer to seeing the world as it really is.